Okay, so we're extremely lucky to have Sebastian Diehl from University of Cologne visiting us for an entire week. So Sebastian has done pioneering work in the field of out of equilibrium quantum dynamics, especially at the interface of quantum optics and many-body physics, which are two fields that are usually not necessarily or historically not together. In particular, his work on field theory techniques in driven dissipative systems have allowed to treat on equal footing quantum effects, interactions, which are important in many body systems, and the drive and dissipation that arises in this context. And so we're hoping to learn a lot about this physics from him this week. So the plan is that he will give 2 official talks, one today, which will be a little more colloquium style, I think, so more kind of focusing on the physics, a bit less on the formalism. Tomorrow, there will be a talk in the Eckert Research Center, which is the building over there, the big shiny building over there at 3 p.m., which will be kind of more research seminar style. And then depending on preferences, we can force him into telling us more things, maybe Blackboard informal talks if we want to know the nitty-gritty details about the formalism. We can kind of see what people want, and feel free to email me or him if you have some preferences about this. But let's get started. So thanks, Sebastian, for visiting us.
Thank you very much, Lucas. It's very good introduction. I mean, it's really a great pleasure to be here. And it's exactly as Luca said. I mean, I'm the whole week, and I'm very happy to also, provide a few more, technical details if this is desired. So today, understanding that there's a broad audience where there's many punctual connections. I still felt it's maybe better to have the physics in the foreground, and then tomorrow I'll zoom into a bit more detail. But for the real technical details, we're very happy to do this maybe in smaller groups like next time. Okay, yeah. So here is my artist's view on driven open quantum matter. You see here the matter flowing, some currents around. It's all coupled to light. And that what makes the drive. And actually, funnily, when yesterday, now it doesn't work again. It just worked. Okay, now it works here. Unshared mode. Say just share.
We are on TV.
How you? Yeah, and now the job is done. It was because it was now the slide builds up. But funnily, when I was yesterday for my little niece looking for a present, then I found this actually personalized version of my anyways artist's vision of driven open quantum matter with direct relation to Chicago. So yeah, let me start very, very basic and ask what is actually a driven open quantum system. And the credit is to be given to the field of quantum optics, where traditionally one looks here at small quantum systems which are immersed into a larger environment, a dissipative environment. So this defines this notion of open. So that means that various physical quantities can be exchanged between the system and this path. For example, energy, particle number, also the flow of entropy can be envisioned. And then the second crucial ingredient here is that the system in addition is driven. So this is actually the push out of equilibrium for these systems. And in quantum optics, this typically happens by laser fields. A very concrete and paradigmatic simple example is the atom approximated by 2 levels here, ground and excited state, and we bridge the huge energy difference between the excited and ground state by a laser with intensity omega here. And then, of course, this atom here is coupled to the radiation field, enabling this spontaneous emission. And a very, very elementary fact is that drive, you see it with your bare eye, is essential to even access this upper level and get a non-trivial dynamics in the system even going. Now, this has two immediate implications. First of all, we observe that there's no guarantee for the principle of detail balance to be obeyed here. If that were the case, I could not have all these dimension energy quantities standing around here, and the rates for going in between the ground and the excited state would have to be determined by just the Boltzmann factors that connect these two levels here. So a second point, maybe not so clearly visible here, is, but in generally very plausible, is that there's no obedience of the second law of thermodynamics in such a driven system, and that can be used in quantum optics for state purification. Yeah? So to get out of equilibrium protocols to push a system into a pure state. Now, how to describe such systems? This is done in terms of these quantum master, also Lindblad equations. So here one focuses entirely on the system density matrix, and the time evolution for the system density matrix is generated by the Hamiltonian governing the system. So this gives coherent unitary evolution. And then the coupling of the system and bath is encoded by means of system operators in terms of these Lindblad operators here. So this is essentially what results in a second order time-dependent perturbation theory, eliminating or integrating out these environmental variables. Yeah? And this index alpha, we leave it free for the moment. It can be spin, it can be a spatial index, and so on. And this entire thing here is referred to as the Lindbladian generator of dynamics. Now, for a simple interpretation, let's just rewrite these terms here and pull this anticommutator here together with the Hamiltonian in just this form. Then you see here the interpretation of this anticommutator term is really something like energy minus the decay that goes on in this system. So this is also referred to then as dissipation. And then in any physically reasonable system, we need to preserve probability. And in quantum mechanics, so we need to preserve the trace of the density operator. And you can remember this factor of 2 in the relative minus sign simply by acknowledging that this quantity here, using the cyclicity of the trace, indeed ensures the probability conservation. And opposed to this dissipation term here, one speaks of the fluctuation that together with dissipation ensures probability conservation.
Is this in some sense a complete description of any open quantum system, or are there systems that cannot be described this way?
It's the most general update on a density matrix if you insist on time locality. Yeah?
Time locality.
In principle, I mean, you can also think of non-Markovian evolutions. Yeah? So, and for example, in an equilibrium problem, if you go to very low temperatures, then this becomes an issue. But this is also the Lindblad, the name Lindblad comes for this problem because this guy was the one who showed that this is the most general time local generator of dynamics compatible with preservation of hermeticity, complete positivity. So a positive density matrix maps into another positive density matrix, and probability conservation. So that's already the answers.
And why it's called Liouvillean?
This comes, I think, from the probability Liouville in classical mechanics, Liouville equation. So I think what is more standard nowadays is Lindbladian indeed. Yeah? So because referring to the guy.
When Lindblad wrote this paper?
I think in the 76, something like that. And there were other people, Kosakowski, Forini. So sometimes it's also Lindblad, Forini, Kosakowski. But on the other side, we have the Martin, Sigia, Rose, Janssen, de Dominicis functional integral. Sorry. Yeah. Anyways, I mean, a lot of names, a lot of famous names. Okay, but so let's go to a just for concreteness, yeah, to fill all these quantities here with concrete formulas for this very simple two-level system. And you see here the Hamiltonian could be represented like that. Here, this is the tuning, so what the laser drive misses to bridge energetically to the upper state, and these are the Rabi, the laser intensity here, and then the spontaneous emission is just the decay from the excited down to the ground state. Okay, so far we have then looked at systems with a few degrees of freedom in the system only, and the task of today is to replace this scenario actually by many degrees of freedom, and that will bring us then to the interface of quantum optics and many-body physics, and give us a notion of really driven open quantum matter. So, and this active matter aspect, I'll get to it probably tomorrow. But what we can already see from here is that these systems here share features from quantum optics, coherent and driven dissipative evolution appear on equal footing. So neglecting either of them would be in order one a mistake. At the same time, so we have these systems now operated with a continuum of spatial degrees of freedom. So this is shared with many-body physics, and this combination then actually allows us to do, or challenges us also to interpolate between the microscopic physics to the macroscopic physics, and asking questions, say, about the nature of phase transitions and really universal questions. So let me point out very briefly platforms in which such physics is actually realized, and the rule of thumb is really whenever, alluding to the picture I had on slide one, whenever you couple light and matter to each other, so then you realize instances of this driven open quantum matter. A beautiful early example is atoms, an entire Bose-Einstein condensate immersed into an optical cavity. In a simple approximation, you can describe the system here by the macroscopic occupation, not only of a single mode as in Bose condensation, but actually two modes. And this gives rise to an effective collective spin degree of freedom. And the coupled matter and light system is then actually to some degree of approximation represented by the famous Dicke model, also of quantum optics, of a collective spin realized by these matter degrees of freedom. Now, a light is also a basis, light by itself, which can realize these driven open systems. For example, these microcavity arrays here. So here the basic player is light confined to these micro cavities here. This can tunnel between different sides, and you can make it self-interact. So to realize versions of the Bose-Hubbard model, of course, I mean, light has this volatile component, and it means that, I mean, you have to pump it incoherently or coherently to ensure a finite density of many-body excitations. Solids are also in the game. For example, these exciton-polariton systems, I'll get to them a little bit later, so let me maybe spare them out here. In the context of atoms, one could also refer to this driven dissipative Rydberg gases, which, for example, realize phenomena like self-organized criticality. And let's also not forget or explicitly incorporate here all these quantum devices that are currently moving up. So of this noisy intermediate scale quantum platforms like the superconducting circuits, the Ansmons. So they were long time the front runner in building quantum computer prototypes. At the moment, they see a strong competition from these Rydberg tweezer arrays, and also in the game are systems of trapped ions. All these systems are never showing perfect unitary dynamics, but drive, dissipation, decoherence, measurement, active measurement of the systems is really crucial for quantitative description of what's going on in the system. So in this talk here, I want to focus precisely on these 2 points that I made on slide 1. I want to focus on these 2 specific features that are specific to this driven open setting. First of all, I want to show how the absence of a second law for this subsystem here can be used in order to generate dissipative dynamics, which establish various forms of quantum mechanical ordering phenomena, for example, conventional phase order, entanglement, topological order. And as a sneak preview, I have one slide lining out a little bit what I will speak about tomorrow. Yeah, so the status of the use of topological concepts in this out of equilibrium dynamics. And the second topic that I would like to address is the absence of detailed balance in these systems. I will point out an interesting connection to the so-called Kardar-Parisi-Zhang equation, and which is obeyed to some degree, but the variant of the KPZ equation encountered here is also slightly different from the original version in that it can host topological defects. And I want to discuss what this means for the long wavelength many-body physics. And that connects me also to tomorrow's talk, where indeed I will discuss this instance of active quantum matter. Okay, good. So let's first look at this concept of order by dissipation. And here is the question, extremely elementary. So at equilibrium, we know that dissipation or friction enhances the statistical degree of this order. The entropy increases by the second law of thermodynamics. And now you can ask whether this can be reversed in a many-body system. Yeah, I mean, in classical physics, this is obvious. Yeah, so your fridge at home is such a transfer of entropy from the subsystem into the environment. And here we would like to ask the same question somewhere in a quantum system. So we want to construct entropy pumps, which really extract it all from the system so that the density matrix thins out to a pure state with hopefully interesting properties. For example, long-range phase coherence, entanglement, or topological order. So a crucial concept for this to work is the concept of a so-called dark state. So just for the simplicity of presentation, we ignore here Hamiltonian contribution. Here it could be reinstalled under certain conditions. But the crucial object or the crucial concept we need here is the one of a dark state. So this is a zero mode of the entire set of these Lindblad operators generating the dissipative evolution. And you can clearly see that when this condition is fulfilled, yeah, so then the time evolution stops when the system has entered this pure state here. The situation is particularly interesting if this dark state solution is actually unique. Yeah? So the picture is then given here. It is then a state that you can enter, but you will never leave it. And you obtain actually a directed motion in Hilbert space, yeah? Absent other solutions and absent parts in Hilbert space where the system cannot escape. The uniqueness of this dark state will make sure that the motion in Hilbert space is really directed. And you can then see that this will lead to this desired feature of dissipation actually removing the entropy, because this condition here is formulated irrespective to the actually initial state, which can be a mixed state. Yeah? So the purity, the late time dynamics definitely increases in such a system. So let's see how this pans out in concrete examples. And for this purpose here, I would like to develop an analogy from quantum optics right over to many-body physics. The inspiration can be drawn really from, not from a maybe two-level system, that's too simple, but already a three-level system can give us here a hint. Yeah? And what is actually done in optical pumping is to consider such a three-level system with two degenerate states down here, and they are driven with an antisymmetric drive with a relative phase between these Rabi frequencies. The decay happens symmetrically. We can change the basis in the system to realize that indeed there is one dark state, yeah, which is really decoupled from the light excitation, and a bright state which still couples. And you can literally see that in this very simple system here, there is a flow, there is a direction in Hilbert space, the system will end up in this state, which is decoupled from the excitation step. And we can translate the basic idea here is now to move from the internal degrees of freedom of an atom to the external degrees of freedom of an atom confined to an optical potential, for example. Yeah? So this could be the unit cell of an optical lattice with two lower sides and an auxiliary side here in the middle. We can arrange to drive the system in this way, and then we reproduce precisely the same situation as with the internal degrees of freedom above. The good advantage of doing this with the external degrees of freedom is the possibility to copy paste this unit cell here many times in space. So you can think of n atoms on m sides, and because the relative phase between each pair of sides is now locked to the positive sign, we will ultimately end up in a state where the relative phase between each pair of sides is locked, and that is nothing but a Bose-Einstein condensed state. Yeah, so this is the Q equals 0 mode, symmetric superposition over the entire lattice, the state that is formulated here. And from that, you can, zoom out and see that indeed it is the combination of drive, of this laser excitation here, and the dissipation, the going down process here, the directed one, that enables the purification. And that does really, in this case, the opposite of decoherence. Namely, it is a way to, by dissipation, generate coherence. So it's a kind of syn-coherence phenomenon. And more concretely, the operators that are at play here are written down here. You can see that this operator here takes the antisymmetric superposition of any wave function on a pair of sides out, couples it intermediately to this upper level here, and then we let it go down in the symmetric superposition. And ultimately, when this process runs all the time, the only state that survives, that passes this evolution, is indeed this BEC state. So in this case, one can actually show that the stationary solution is unique, and therefore from an arbitrary initial state, be it as mixed as it wants, you will reach this BEC state in the long time limit. And experimentally, this has actually been realized, or something like that. For example, entanglement generation in a system of 4 ions here, like a few years back. And more recently, people are exploring this concept here also in these NISQ platforms. For example, the AI collaboration recently went to 18 sites, I think, and could also show that, such a dissipative, engineered dissipative protocol, you really can push the density matrix into a pure state with, for example, interesting long-range quantum correlations. Okay, let's then zoom in on something else, where other states can be targeted in this way. Topological states. Here's a superficial slide on that, just to remind you of the basic concept, or the way how I want to speak about that, what I mean here. So this topological order is beyond the Landau paradigm of locally visible order parameters. The information on the order is encoded here in the global properties of the manifold, and then not so easy to look to see locally. While, of course, there's part of the interest is that there's still observable consequences, like boundary correspondence, for example, tells you that there's robust edge states, which in turn can carry interesting exchange statistics and thereby become candidates long run for topological quantum memories on computing. Systems are archetypical quantum Hall systems, and of course also topological insulators and superconductors. Now, the question I would like to ask here are twofold. First, kind of a practical, in the light of also this growing, NISQ platforms. Can one find protocol out of equilibrium pooling protocols that targetedly prepare interesting and relevant, computationally relevant states of matter? And then a bit more conceptually, whether these concepts coming from topology, they are usually really formulated for wave functions in the ground states of Hamiltonian. To what extent are they useful or robust, including for non-equilibrium and maybe mixed states. So that's probably what I get to more tomorrow. But here is just a very basic example. I want to construct this example again from something that is very well known, like this Kittief's quantum wire. So this is the Hamiltonian scenario, 0 temperature now, and a model that is topological, can be topologically non-trivial, is this p-wave superfluid Hamiltonian in one dimension. Just we have a single particle hopping. We have a, for example, a proximity-induced off-diagonal term here, and something that represents Cooper pairing and the chemical potential to regulate the mean filling of this wire. And you can obviously diagonalize this Hamiltonian. There's two specifically simple and transparent representative limits, namely one limit in which the eigenoperators, where the Hamiltonian is diagonal in the basis of on-site local fermion creation and annihilation operators here. This is referred to as the trivial phase, the atomic limit really, and you can graphically represent this by introducing for these complex fermions, Majorana fermions, represent this kind of local, completely local atomic limit here by energetic links on each side here. The second representative is quasi-local, so the eigenoperators extend now over two sides. And you can see here the use of this notation here. Now the energetic links, they really connect the physical sides to each other. And you can literally see here two isolated without links means sitting at 0 energy states, Majorana fermions at the edges of this wire here. So the bulk of this problem here is the BCS P-wave superfluid, and the edge has these unpaired Majorana modes or a non-local fermion in the complex Bogoliubov language. Now let's think about how we could do this, how we can get to such states using dissipation. And to this end, I would just invite you to reconsider these operators that I was formulating previously for the BEC state. So they are a product of an annihilation and the creation part here. And an interesting insight was that if we have these operators here as bosonic operators, then the dark state will be a BEC state with a fixed particle number. While if we just interpret these guys here as fermionic operators, then the dark state is actually a BCS wave function with a fixed particle number. And this concept works beyond this specific example that I was introducing with this operator. But if you choose exactly this constellation of operators, then the wave function that is dissipatively induced in this setting here is the Kitaev ground state wave function for a fixed particle number. So to see then even more clearly the connection to these fixed phase wave functions that are typically considered in superconductivity, we can appeal to ensemble equivalence and move from the fixed number operators here. So this operator just reshuffles the superposition of a single fermion. That means it commutes with total particle number. But we find that, appealing to ensemble equivalence at late times, we can linearize the dynamics, the nonlinear quantum dynamics generated by these operators here. And they actually linearize in this way. The product of annihilation and creation part transforms into a sum of these two operators. And these are precisely, indeed, these Kitaev Majorana operators that we were looking at previously. So from that, we can conclude so that indeed the dark state of this evolution is a Kitaev P-wave superfluid as the one that can be obtained as a ground state of a Hamiltonian. So as a
late time approximation, you're saying they just have the same dark states, therefore you can approximate them.
Yes, so you can, right? You can run this dynamics for a fixed particle number, then this is a solution. Of course, you can also allow any kind of superposition of particle numbers, and that will also be solutions. Yeah? And especially also this, this state that is equivalent in the, the fixed phase representation of a fixed number state goes via this Fourier transformation of the state. Yeah? So you, instead of fixing n, you fix now the phase. And that is also a solution of this equation. Yeah? And that is a way how one can show that. Yeah? So it's definitely also a solution of that. And yeah. Okay. So as a small sneak preview, so there has been quite some work along these lines. Yeah? So for example, different insulating and superconducting states have been constructed in this way, and there's also some work of implementing this concept in Majorana devices. So on the conceptual side, what I would like to stress tomorrow is that, these concepts of topology, indeed, in the context of pure states, they are stronger than dynamic concepts. Yeah? So equilibrium versus non-equilibrium generators of dynamics. For example, one can see that the topological response that sits on top of such a dissipatively stabilized insulated, say, Chern insulating state is really exactly the same as sits on top of a Hamiltonian ground state. And kind of at first sight, I found this pretty surprising because it tells you that there's a kind of a reversible response protected by topology, which sits on top of a totally irreversibly evolving bulk, and it includes also the existence of a bulk boundary correspondence for this system. Moreover, one can see that topology also beats the mixedness of the state in the sense that one can still formulate observable and topologically quantized invariants, so including at finite temperatures or in mixed quantum state, and that can be formulated for all symmetry classes. And we can formulate this insight here in terms of a topological field theory for mixed quantum states in and out of equilibrium. So that would be part of what I will discuss tomorrow.
Sebastian, can I ask you a brief question on this part? The idea of the dark state seems to me somewhat similar to the notion of an absorbing state that exists in classical system, and similar consideration can apply there. Is there and I understand that if you arrange your absorbing state to be a quantum state with a special property, you're going to get quantum property being singled out. Is there anything inherently quantum in the mechanism that leads to the selection of state that I can't really see by analogy to my, say, simple absorbing state?
I think the answer is, what is the nature of this absorbing state? Yeah? For example,
so it's the nature, not the mechanism of selection.
You are the mechanism. The statement is you can prepare entangled states, states with phase coherence, states with topological order, but the fact that there are dynamical generators that annihilate specific states, that to that level it's the same. Yeah, but I think on that level you could basically always compare quantum and classical mechanics. And so I think it's mainly about the resources. And so that you might benefit from when you apply this quantum selection. And it's actually a very interesting topic for example, if some experts maybe have heard about these measurement-induced phase transitions. Yeah? So they can actually also be related, to absorbing state transitions. So the strongly measured regime here is very closely connected to absorbing states.
Thank you.
Okay, good. So let me change gears and now look at the phase structure of low-dimensional driven open quantum systems. And here I would like to remind you of the beautiful universality encountered in low-dimensional quantum systems. Yeah? So, for example, if they are equipped with a continuous phase rotation symmetry, like atomic bosons or planar magnets or so, then at low temperature, one universally has 2 dimensions, and correlations decaying algebraically versus at high temperature exponentially, while there is a superfluid response in the low temperature regime and it goes away at high temperatures. And this interpolation here, so some qualitatively distinct behavior in 2 regimes, this goes via a phase transition, the famous Kosterlitz-Thouless phase transition of unbinding vortex and anti-vortex pairs. So what we want to understand now, so what the fate of this scenario is out of equilibrium, and if there might be some new phenomena tied to the very non-equilibrium nature of these systems. And the main results, so this is kind of a caveat, and the Kosterlitz-Thouless transition itself will be, as a matter of principle, unstable towards the slightest non-equilibrium perturbation, protected by an exponentially large scale, however, and for weak out of equilibrium perturbation. And there is also something new indeed coming in, namely a phase transition, which is just driven by pushing the system more and more strongly out of equilibrium. And the platform that is useful to think about here are these exciton-polariton systems. So here one has these excitonic electron hole pairs here, the degrees of freedom which have a very flat energy momentum relation here. And then you have photons bouncing back and forth in these reflecting mirrors here, which due to the confinement in the z direction have a basically quadratic dispersion. And one can now hybridize light and matter, coupling them strongly to each other to finally get an effective hybridized dispersion, which is this full gray line here. One then can then pump the system, for example, with a laser targeting here occupation of this upper polariton band by a cascade of decay processes here. The system will finally settle down in the most stable state of the system, is lower polariton degrees of freedom, but nothing is perfect. So particles will also be lost from here. And a simple phenomenological description for this problem here is written down here. It's a kind of phi force dynamics here, or driven dissipative Kosterlitz equation, where you have here a propagation term. You have here the single particle pump, incoherent pumping, that's this process here, the loss rate. And of course, these particles, they can elastically collide, or they can also be lost in pairs, so giving rise to some two-body loss. The key point I want to emphasize here is that coherent and driven dissipative dynamics really occur on an equal footing. So every reversible or elastic process here comes with a irreversible counterpart here.
So can you mention what is this two-body loss, the nonlinear dissipative term? What's the meaning of that?
Where it comes from?
Yeah.
I mean, you can think of it in a RG way of thinking about it. It would be just allowed by the U1 phase rotation symmetry of the problem. Then it would be pretty small. But so there's nothing that would forbid it. And for the arguments I want to make here, it's actually not. It's actually the size is actually not crucial. Actually, these systems often have, in fact, a very small elastic collision. So they actually, in fact, the two-body losses they might even dominate in this sector. Okay. So in these systems, it has been established that they can Bose condense, despite the fact that we have here non-equilibrium conditions. And this is indeed very simply encoded in this equation here. You can see it when we neglect everything that makes life complicated here. When we go to a deterministic limit, we ignore the spatial dependence and look for a stationary solution of this simple equation, and you get the intuitive result here that whenever the single particle pumping exceeds the losses, then the system seeks a new condensed stationary state, and the system starts to build up some amplitude of this polariton field here.
So there is an I in front of gamma P
Right.
minus gamma L. How does phi?
Very good. So you can decompose this equation over real and imaginary parts. And then what determines, it's very intuitive, what determines the state of the system is the imaginary part. So this gives you how strongly, or this describes how strongly you pump, how big the losses are. And then you have this parameter mu, which is basically a rotating frame. You maybe shouldn't think of it as a chemical potential that regulates something, but rather as a parameter that the system can choose to accommodate also the real part of this equation. But the physics is, of course, so that the decay processes, they determine, so how big is your condensate. Okay. Naively, so this looks very much like Bose condensation and equilibrium. So let's now zoom in on the question, in which sense this actually describes really a non-equilibrium situation.
So that's ignoring the noise.
Sorry?
That's ignoring the stochastic noise.
We ignored it just for the matter of explaining, so like the very basic physics. And next we want to include this. And all I'm going to say now does not work absent noise. And so the noise is really crucial. It's just to get an orientation. So at zero order we do this, and now we come to more complex things. So to see in which sense the systems here really describe out of equilibrium states, we can decompose this Kostka-Evsky equation here into this generator of reversible dynamics and the irreversible dynamics here, and each of them is chosen in accord with the U1 phase rotation symmetry that this problem enjoys as a kind of Landau-Ginzburg theory. And we can then plot the couplings of these coupling constants here in a complex plane where the imaginary part is associated with couplings encoded in this dissipative generator here, and the real parts are encoded in this reversible generator here. So for an example, if we look at this two-body processes that I was referring previously, and so the real part would be of the two-body sector would be the elastic collision rate, and the imaginary part is two-body loss rate that we were just discussing. Now, the interesting point is, so that this is actually the watershed between equilibrium and non-equilibrium generators of dynamics, which one can see if one maps, for example, this stochastic Kostka-Evsky equation into a functional integral representation, fully equivalent. And then it is known that the thermal equilibrium conditions in such generating functionals here are encoded in terms of a special symmetry. So equilibrium conditions are encoded in a symmetry, and the word identities of this symmetry are really just fluctuation dissipation theorems of arbitrary order. In other words, you can think of the conditions of thermal equilibrium in terms of a symmetry. And if you apply this symmetry consideration to the functional integral associated to the stochastic dynamics I was just pointing at previously, after everything has been said and done, you can see that in the presence of the equilibrium symmetry or in the presence of detailed balance, now all these real and imaginary parts, they have to be pinned on a single ray in this complex plane. So this is protected by equilibrium symmetry, and this is the non-equilibrium situation, and this is actually the right way of thinking about the distinction of equilibrium versus non-equilibrium Bose condensation, at least on this mesoscopic level of description. And there is a very good intuition behind this. In an equilibrium problem, certainly you can have irreversible dynamics, but these irreversible dynamics, it basically comes from a renormalization process that has started somewhere here on the real axis, on the microscopic level. We just had a Hamiltonian generator of dynamics, and we coarse grain that. What it does is that it just rotates all the couplings out into this plane. So here would be the totally dissipative asymptotic long wavelength limit, while in a non-equilibrium situation, so the coherent, the reversible and the irreversible dynamics, they are just totally unrelated to each other. And they come from very different dynamical resources, and there's no reason why they should obey any special relation with respect to each other. And the question that we want to ask now is what the physical consequences of this spread in the complex plane of couplings actually
Sebastian, do you mind spending a few more words in explaining what the dynamical symmetry is?
Yeah. Right. I mean,
Maybe you did and I didn't.
No,
completely got it.
not in detail. Yeah, so you can transform this Langevin equation into a functional integral formulation of the problem. So that's that thing. And then you can, I mean, it's maybe better in the quantum system to see where this comes from. In quantum systems, we have the Kubo-Martin-Schwinger relation. Yeah, and that is something that is a relation that is present when the stationary state of the system, e to the minus beta h, is generated by a time-independent Hamiltonian generator of dynamics. So if the generator of dynamics is a time-independent Hamiltonian, then, I mean, a thermal state is an equilibrium state of the problem. And under this circumstance, yeah, when the generator of dynamics coincides with the object that governs the stationary state with the Gibbs distribution, then we are in a state of equilibrium, which obeys this KMS relation.
Oh, I see. So the dynamic symmetry is just an equilibrium problem.
Right. Yeah. And this is really the key point. Yeah. So then you have
So
this.
what do you call a dynamical symmetry?
I mean, because I mean
the symmetry in
so,
standard sense.
so,
I thought there was
so
something characterizing potentially a non-equilibrium system too.
but yeah, I mean, we use this as a feature. We have a symmetry, a discrete symmetry transformation, which is present whenever there's a KMS relation. And the point is then that it gives us a handle of distinguishing. Yeah, you give me an action, you give me a generator of dynamics, and I can check is this symmetry present, and if not, then I'm in an out of equilibrium situation. And that's very helpful, yeah, because I mean we can then ask, yes, so we have then a sharp distinction, but the symmetry is only present if the system is at equilibrium. And then we can watch what these couplings are doing under further force plaining, under further renormalization. Sometimes you have emergent equilibrium at long wavelengths. Yeah? So then these situations here, they come close together. Or tomorrow I will tell about an example where it's exactly the opposite is the phenomenon takes place. And so that you perturb a little bit out of equilibrium with a little spread, this becomes worse and worse. And so the asymptotic long wavelength properties are then strongly non-equilibrium. But in that sense, it's a useful razor, yeah, to diagnose how close at this given scale, yeah, the system is to thermal equilibrium.
Yeah, so in the system you were describing, you had this U1 symmetry of rotating
Yeah.
the fields. This is valid whether you have the dissipative term or not. That symmetry is always there. The symmetry that you're talking here that is broken is this KMS symmetry.
Yes,
right?
Mm-hmm.
But this is like an explicit breaking of the KMS, right? When you put that extra term, it breaks. So it's not like spontaneous breaking anyway.
No, this is it's an interesting question. Yeah, if there can be a spontaneous breaking of the symmetry, I would say whenever a system fails to thermalize, so then there's no reason to think that the field theory that sits on top of such a state, which is not thermalized, should obey this symmetry here. But in general, it's right. I mean that I view this symmetry mainly as a diagnostic tool to precisely define whether a given action or a given problem resides at thermal equilibrium or not.
I see. So if you're doing effective field theory, you can see which terms would I put the break KMS condition. This would be non-equilibrium terms.
Exactly. I can dial in based on this diagnostic tool. I can dial in. I want the system to be out of equilibrium. I can put a little seed of non-equilibriumness. Yeah, and the logic is then always to ask, I mean, if it's about finding macroscopic universal non-equilibrium phenomena, I want to zoom in on situations where this breaking of the symmetry becomes worse and worse. Yeah, the larger and larger you go in size.
And just a bit confused about this plane. So this is a real imaginary plots of your field of phi?
No.
So
No. So I mean, this is really. Maybe I have that. Yeah. So here we have these two generators of dynamics.
Okay.
So this is the reversible, the irreversible one, and each of them I can write. I mean, according to the U1 symmetry by Landau-Ginzburg functional. And then, I mean, I ignore dimensions of these couplings in this plane. Yeah, but I can just make a cross here whenever there's an imaginary part which is finite. Yeah, say for the R term. finite imaginary part, I put it here, and the real part, I put it there.
All right,
So it's not the same
blue is
dimension.
The conservative part and the orange is the dissipative part. Is that correct?
The real part here is the conservative or the reversible part, and the imaginary part here is the irreversible. So, but what is correct is that, I mean, you shouldn't apply dimensional labels to this, because I mean all the couplings are in the same plane here. But what is true, what is the characteristic feature of an equilibrium problem is that the ratio of all these couplings, which always is dimensionless, that this is one and the same for all couplings you might be able to formulate. So the ratio is always something that dimensionless, and they have to be all proportional to each other. That's the special implication, the geometric implication, if you like, of the presence of this thermal symmetry in this semi-classical limit of the problem. So I could have derived this equation from a Lindblad equation by taking a semi-classical.
Can you comment on the connection potential between your dynamical symmetry and the entropy production rate?
Right. Very interesting. We are actually looking at this at the moment, and it turns out, I mean, the entropy production, we're looking at this entropy production near a critical point. And it takes the form of something like the length scale of this problem to some exponent times a dimensionless function, which has to be exactly 0 if you require the equilibrium condition. So this is precisely an interesting application of this dynamical symmetry. No entropy production if the symmetry is present, precisely this. Thank you.
Okay, you implicitly restricting, I think, to interactions that come from a Lagrangian or Hamiltonian with the dissipated terms.
I view this really as a kind of give me a Landau-Ginzburg functional. I mean, the H, naming it H is arbitrary. So it's not a
I mean, even the equation of motion above, it's a variation of something.
Yeah.
As opposed to these some interactions that were not coming from a very
right. Yeah, and so
it's
right.
A special case of like a non-active matter system in some sense.
It is in some sense a special case. If you go to a real basis for this problem, you see that actually this thing here comes with a unit matrix, and this one comes with an epsilon ij. And then you see in this that it's not a variation of a real scalar function,
But a complex scalar.
but a complex scalar function. Or maybe the more structured answer is if you go to real basis, like the ON models, I will discuss this tomorrow. And then you see actually that indeed this term here, I mean, is not both terms can be written as a derivative of a single scalar potential function. Because you have two matrices, a unit matrix and an epsilon ij. Very good. Right. I mean, this usual, I mean, it's conservative. You can write it as a derivative of something that assumes real valued functionals. So that's, I mean, which give you a weight, a statistical weight in a semi-S or a Gibbs weight. Imaginary doesn't make sense. So it's oscillatory weight. So if you want to look at it on that thing. Yes. Okay, very good. So now we want to track what the physical consequences of this spread in the complex plane actually are. And so in this case, it's a super simple exercise, just to choose a phase amplitude decomposition and realize that the amplitude fluctuations in such a symmetry breaking situation, they are decaying very fast, they are evolving very fast, and you can integrate them out to just focus on the really kind of, this is such an intermediate integrating step here to focus on the slowest variables in this problem. And then you can realize that the equation that comes out governing the phase dynamics precisely coincides with the famous Kardar-Parisi-Zhang equation formally. So, and that means here physically that this diffusive spin wave that is described by this part of the equation receives now a non-linearity. And this non-linearity is a single parameter measure that's a very comfortable situation which allows to zoom in many details in simple setting, in a simple setting, is that this single parameter here measures the strength of non-equilibrium conditions. In this circumstance, where we have equilibrium, at least in generic dimensions, so this lambda parameter has to be exactly 0. It is excluded by presence of this thermal symmetry, while, I mean, in a non-equilibrium scenario, generically, this lambda parameter will be non-zero.
Question. Yeah. So you've probably assumed something about the statistics of your noise to make the statement about the phase, because generically KMS is not enough to guarantee that you know, they all have the same angle, all the couplings have the same angle in the complex plane if the noise is non-Gaussian, right? So I guess you've assumed.
For the noise, I mean, we always assume it's white noise, yeah? An assumption which is good under the following circumstance. Yeah, when we look at, I mean, when we look at energies or frequency scales which are well below the average noise level, and so everything looks like a delta function. So for the slow variables that are evolving on frequency scale way below the noise level scale, which is also dimension of energy, and so basically the noise always is very fast or looks delta correlated.
I guess that's another source of slightly different angles, even in equilibrium contexts, if you know you're not at asymptotically small frequencies.
Yeah. No, I think that it's with respect to the discussion we had in the morning, or.
But no, just a general comment that I think there's a way. Yeah. Okay, but maybe it's
okay. So that would be something to discuss in more detail. So yeah. Okay, I think, I mean, for this consideration, what should be really kept is that, I mean, 1D is a special case if you have this in mind. So 1D is very special, but I mean, in general, I would really think that this is a pretty sharp criterion. Okay. Okay, let me just slide on this KPZ equation. So where this comes from is the position of particles in the presence of noise. So you can have this picture of a tilted interface here, where you deposit particles at a rate lambda in a gravitational field here. Now this equation is written already in a frame which co-moves with the growing interface, and then the dynamics on top of this interface is actually this smoothening trend of diffusive dynamics and this roughening trend of this nonlinear term. And why it is famous? Well, it has actually really multiple physical contexts. The best experimental verifications in these classical systems is defect growth in liquid crystals, which are driven by an electric field. But I mean, in principle, also problems like bacterial colony growth, so driven problem, or the spreading of fire are in this universality class.
So going back to your comment about the non-potentiality.
Yeah.
Is the right-hand side of that equation not writable as a functional derivative
of a complex function?
Is that dynamical system potential or non-potential?
It's not potential in the sense you cannot formulate a single scale, real
There's
scalar
not a
function.
variation of phi or theta.
Not of a real scalar function.
real
So I mean, we had these two.
Because of the lambda term, even in the absence of noise.
So this equation, no, the lambda term is not represented.
It's not even when the noise is. So that's where the connection to the other.
Yeah. Well, I think in this classical limit, so the non-conservativeness of terms and the presence of the thermal symmetry, that's really the same thing. In the semi-classical limit, which we are discussing here. Okay, so in the crucial step now, we want to start from this intermediate scale dynamics and move to the macroscopic scale to assess actually what the consequences of this spread or the breaking of equilibrium conditions or the spread in the complex plane actually are. And here is what happens here. So this is the known flow of the KPZ equation, one loop flow, and the structure is like that. As a function of dimension, there is an important trend in high dimensions. If you initialize your system slightly out of equilibrium, then equilibrium conditions will be restored. So you're flowing to lambda equals 0, which means you're flowing to equilibrium. But in low dimensions, starting from 2, the non-equilibrium perturbation is marginally relevant or relevant, and the system, even if only slightly perturbed out of equilibrium, finds a strong coupling KPZ fixed point. And the scale where the deviation from equilibrium becomes sizable can be estimated by asking when does this dimensionless flow parameter here reach order 1, and you see then for a weak non-equilibrium perturbation, and so the scale in 2 dimensions is exponentially large. And that gives then rise to the following structure of the 2-point correlation function for this problem. At small enough distances, the decay of the correlation function is still algebraic, as you expect from an equilibrium problem. But the asymptotic behavior of the correlation function is governed already by the strong coupling KPZ fixed point and shows this stretch exponential behavior here. And these 2 regimes here are separated by this length scale, which for weak non-equilibrium drive is, however, exponentially large.
So sorry, there you initialize the system in some state, more or less close to equilibrium or some perturbation in 1 dimension. As the time evolves, it gets to this strong coupling fixed point. No, so time evolution is
RG time evolution.
RG.
Sorry, yeah, so that, I mean, and when I say perturbing out of equilibrium, I don't have in mind a dynamical protocol of hitting the system and then like a linear response idea. That's not the way I want to think about that. I want to think about it is, I mean, do we have some exciton-polariton systems, for example, which, I mean, where the system is somehow confused which reservoir to thermalize to, because you couple it to multiple reservoirs, and in this way you prohibit the system from self-equilibrating. Yeah. So that is the key point. Okay, right. So to summarize this here, the algebraic order in this problem is absent in basically any 2-dimensional driven open system at the largest distances. However, the scale is exponentially large, and that is why you don't have to fear now that every 2-dimensional system will behave in crazy ways. On the other hand, I mean, in 1-dimensional systems, where the same reasoning about equilibrium versus non-equilibrium holds, indeed, this KPZ scaling exponent here, dynamic KPZ scaling exponent, recently has been observed. Yeah, so in 1 dimension, the situation is a little bit more forgiving because the scale is not exponentially large, but just algebraic in the microscopic parameters. So finally, I would like to discuss the fate of the Kosterlitz-Thouless transition in this out of equilibrium context. Yeah? And one has to realize, so that is takes the form of an ordinary KPZ equation, but it is also true that this variable here is a phase. So it is not an interface that grows from 0 to infinity, but it's actually a compact variable, and so it repeats after every 2 pi. And this is has crucial physical implications. Namely, it allows for the formation of vortex defects. Yeah? And this is in fact what really drives the whole phase transition in equilibrium already. The Kosterlitz-Thouless transition is basically the physics of an energy dominance, where the binding of a vortex-anti-vortex pair wins, which is only beaten by a strong entropy gain, which you benefit from if temperature is sufficiently large. And now we want to understand this compact KPZ equation, which looks the same, but of course has a periodic boundary condition. So we need to find a way to deal with that. And the way how we do that is inspired really by the equilibrium problem, where one can, for example, map this problem here to a 2D Coulomb gas, so an electrostatic approach to this problem, and then studies the RG flow. So what we did here is essentially to formulate a nonlinear electrodynamic problem for this theory. And its analysis shows the following feature here. So if we look at we compute the interaction potential between a vortex and an anti-vortex in equilibrium. This is this logarithmic potential, which is always growing. So it's always attractive. But we find here that there is a non-equilibrium correction coming in at order non-equilibrium perturbation lambda squared, which has the opposite sign here. and leads actually to at large distances to an unbinding of these vortices. Yeah? And there's another exponentially large length scale then in this problem, which is different from the one that I was telling you previously. Yeah.
It's not entirely obvious to me that in a system that is non-potential, the interaction between the topological defect would have a potential as opposed to a force.
Yeah. Mm-hmm.
Did you check this point
So,
carefully?
yeah. At lambda, there is, also at this order in lambda, it's absolutely correct, but the only contribution that comes in is of the potential type.
That's a perturbative result.
Yeah, that's a perturbative in lambda result.
So did you check if non-perturbatively there is a component of the force between two vortices that cannot be written as a gradient to a potential with respect to the distance between them?
I mean, I would not know how to do that. I mean, analytically. I mean, so analytically we expand, so to say, order by order in this lambda.
Is that the first order in lambda squared?
Yeah, it's a first non-trivial contribution.
What if you go to lambda with d to the power of 4? Is there a force?
That
For example, I know that in generalization of elasticity, that are non-potential, dislocations do not have an interaction via potential. You will have also, say, transverse forces that cannot be written like that.
No, I mean, I agree that this could in principle happen. I mean, in this problem, I mean, at least at order lambda square, but I mean, it's a fair point. Yeah? So
it's a question. I
don't know, but I mean, we don't have the answer. I can only say at order lambda square. It's like that, and already this calculation was not so simple. So, I mean, we stopped at the order lambda square. So, I mean, you can say many things. Yeah? So maybe at order lambda 4, it curves up again. Yeah? So, and then you get a sequence. But I mean, this is a perturbative result, order lambda square.
What happens if you set d equals 0 from the start? Can you actually
d equals 0?
Yeah. Can you study that dynamical system only with the non-potential part? Have you tried?
I mean, we tried that on a lattice, and that gives actually interesting effects. So that then this with this term only, so there is actually on the lattice there is actually an interesting emergent Liouville theorem, which means that which is interesting in the following sense. You can then say that all the fixed points of the dynamics are either elliptic or hyperbolic. And such systems, I mean, they behave strongly chaotic. And while this term here, I mean, it stabilizes. So this has a stable attractor, but this term by itself, it really has a structure that makes the system, I mean, behave chaotically.
Because you could put just two defects.
Yeah.
And then evolve it only with d equals 0 with the other term and see what, what happens to the dynamics of that. You may see just by eye that.
Yeah, I mean, you will see that this becomes turbulent. Yeah. So, I mean,
or chaotic.
Chaotic, Exactly. But in this perturbative calculation, you can feed this this potential here into the Koselleck's, or you can, I mean, study the corrections to the BKT flow equations here, and you see that indeed this kind of from this picture expected phenomenon, so that the flow for a long RG time wants to go to this fixed point, where lambda is where the fugacity is 0 and where the system is ordered, actually finally runs off, and that is really kind of the signature of activation and noise activation of this vortex pair to this scale here, and then deterministic unbinding. So this is a kind of activation or thermal or noise activation of this vortex anti-vortex pairs, which then finally leads to a runoff, and it conceptually again destroys the BKT behavior at another exponentially large scale of the problem. Okay, so we see that this is fragile to non-equilibrium perturbations. Now, it is kind of an analysis that is really restricted to very small lambda. So we are working perturbatively here in lambda. So we are working essentially on this noise level axis and very small lambda. And one would like now to know what's, for example, the physics that pops up if we go here very far off the equilibrium problem. And to this end, we can look at this 1 + 1 dimensional problem. and that is here the result, I mean, from a numerical analysis. So in this small lambda regime, we see down here at low noise level, the KBZ scaling behavior. And if we go at low noise level in this direction and go to strong lambda, then indeed we go into this vortex turbulent regime, which is kind of, well, easy to understand in this extreme limit out here. I mean, while we actually don't have a good analytical understanding of this phase transition here, but the qualitative physics is really onset of turbulence.
What does vortex and what does turbulence mean?
Right.
In 1+1
In this 1+1 dimensions, it's essentially a vortex that is the dynamics of phase slips. And so if you start from a flat profile, it's a kink. I mean, in space, it's really the development of a kink. Yes, we have periodic boundary conditions, and the boundary condition jumps by 2 pi. So, and the only way that this can proceed as a dynamical process is by having a singularity somewhere in the space and time plane. So in that sense, in this
it's like a Frankel control model, it's like a slip, it's a model of friction, a slip.
So maybe there you can.
And what does turbulence means?
Turbulence means technically that, I mean, if you look at the 2-point function, sorry,
Power
at the
function.
occupation function, for example, single particle occupation function in this problem, then you, I mean, starting from this Kospitayevsky equation, you have a well-defined meaning of how modes are occupied, mode occupation function, and I view this here as the long wavelength limit, which causes this. Then you see here power laws, which are absolutely not the expected 1/q square occupation, and they have heavy tails, and that is the typical signatures of that. I mean, that is of course not clear in these pictures, but you can at least see. So what happens here? So here you see all these defects popping up. And so once you operate the system.
So it's like defect chaos.
Yeah, defect chaos. Yeah. So there is subtle, I mean, how to rank this. Yeah, and I mean, yeah, so that is something that I mean, we didn't look at. I mean, there's manifold forms of this chaotic instabilities, which precisely it corresponds to.
So these pictures are from numerical analysis?
Yeah. Yeah. Okay, and this transition here, it also it is a first order transition. Yeah? So if you go this way here, actually you jump by orders of magnitude. Yeah? So there's a probability of finding vortices in this plane. Okay, so as a sneak preview for tomorrow, and sorry, I'm really quite over time here. So one could make the point that the quantum materials, they are usually really hard to drive away from equilibrium, and the most natural scenario that you see, because a system tends to relax to equilibrium, is even if you look at systems that are, one is say at equilibrium and the other one is at non-equilibrium, then at long wavelengths, you have an emergent equilibrium scenario. And an interesting question is actually whether you can initialize a system at equilibrium and far a little bit out of equilibrium and then have this scenario here. And what we can read this result here as is that indeed, if you have soft modes in the game, like this Goldstone mode that become nonlinear due to this KBZ interaction strength, under this circumstance, actually a weak non-equilibrium perturbation can lead to very strong macroscopic phenomena. So like the completely qualitatively modified scaling here. And what I want to speak about tomorrow is that actually if one looks at this a bit more systematically from the viewpoint of ON models, so really the workhorses of statistical mechanics, and places them out of equilibrium by just violating explicitly the thermal symmetry, and one operates this in the vicinity of the onset of a time crystalline or time translation symmetry breaking transition. So then actually we free here indeed totally mechanisms of this type, which might be interesting for, I mean, both I find it kind of conceptually interesting as so whenever time translation symmetry is broken, then we have to expect such a phenomenon here. And it's also something that one could follow up in experiments. So with this, I'm at the end of my presentation method. Just thank you for your attention.
Okay, so we had a few questions, or we can take a few more.
So maybe a question about the second part of the talk. So when you talk about KPZ versus Costa-Stables, when you focus on correlation functions, is there something to be said about the superfluid density? Like there's a difference between different cases, and what would be, like in an experiment, for example, what would be a good sort of measure of the superfluidity density?
Right. I mean, it's a long time ago, but we looked actually at the superfluid response, and we found that this is actually stable under this. So there would be a, I mean, indeed, you're right. Yeah. So out of equilibrium, not all things have to, I mean, correspond one-to-one to the phenomenology of the equilibrium problem. And we actually looked at the superfluid response, and this stays stable. Yeah, in the
Stable in the one phase.
In the low temperature regime, yeah? So, or in the low noise level regime. So there should still be a superfluid response, and possibly also a transition to a regime where there's no such response. So, and the protocol that we use is really this kind of stirring. Yeah. So that has a superfluid response.
If you have a paper on that, I want to say. If you have a paper on that.
Actually, yeah, I think we somehow didn't write it up. But I mean, I can look up the calculation somewhere. Yeah.
I wanted to ask a question about the Kitaev chain example you discussed. What does that hold in general for like any SPD phase? If I have a lattice model, I can write down a Lindbladian that sort of will have that as a equilibrium phase.
Yeah, I mean, you can, I mean, there is a kind of, I mean, if you give me a BCS wave function or a topological insulator wave function, there's always a way to find a parent Lindbladian, if you like, that would annihilate that state. I mean, as long as it's a Gaussian state. So precisely the class of, I mean, the target class of systems that are also for this SPT matter. Yeah? So for all these scenarios, you can find these parent Lindbladians. There's one caveat, and that is that, I mean, for example, if you have, or it's an important one, if you have a two-dimensional Chern insulator, for example, so there's an obstruction of choosing this Lindblad operators local. So you have to go, in that case, if you want to prepare, I mean, for example, Chern superfluid in 2 dimensions. So then actually you have to go to non-local Lindblad operators.
But in those cases, because they're saying that for every kind of lattice system that I can have, I can find this parent Lindblad operator, but what's the meaning of this operator? Which kind of heat path do you use to construct that? Because generically, the way I'm used to think about Lindblad is that I have a system, I can put you a bath, I have some properties of the bath can be ohmic or not, and then I get Lindbladian. But you're kind of going the other route. You're getting the Lindblad that would satisfy the physics that you're interested in. So do you know like which bath I should couple the system together?
I mean, you can always, I mean, at least in your mind, unintegrate the Lindblad equation. Yeah, so unintegrate the bath that leads to the Lindblad equation. And then you can formulate a Hamiltonian that, I mean, where these Lindblad operators show up in the system bath coupling. So in that sense, I mean, it's a choice of wave function, choice of Lindblad operator, unintegrating the bath, then you see how you have to couple your bath to the different ingredients in the Lindblad operators. I mean, it's a bit a nested process, so there's this hierarchy of scales, but there is definitely a clear-cut program of connecting one to the other.
Integrating the bath, it seems kind of a hard operation for me. Like
no. I mean, not physically, but you're asking. I mean, I understood you're asking about the structure.
Yeah.
So, so if you want to know, so how would I have to choose a system bath coupling in order to engineer this and that Lindblad operators? Then it would be there's definitely a clear path how to formulate that system bath Hamiltonian that will ultimately lead to this dark state, to this Lindblad with a certain given dark state. Okay, I mean, you have to basically think about this this process of, I mean, you have a target system and this auxiliary system. We want to excite the system to these auxiliary sites, and then you have to couple. So this is one part, and so there needs to be a drive part from the target system to the auxiliary system. The auxiliary system is coupled to a bath, and then you integrate out first the bath, and second these auxiliary sites, and then you'll end up with this Lindblad. So this, I mean, this is a very clean derivation. Yeah, how easy that is to get in an actual experiment, that's a different story. But I mean, the structure of the system bath coupling Hamiltonian, that is clear.
Any final questions?
Just to confirm, did you say that the KMS symmetry was enough? Like if you broke the KMS symmetry, you would go to a non-equilibrium?
Sorry, can you say that?
Did you say that if we break KMS symmetry, then you would not be in a thermal state anymore and would have that?
I mean, if we break the KMS symmetry, yeah, so then we are in a situation where in principle, I mean, yeah, detailed balance is broken. Yeah? But that doesn't tell you automatically that we will see giant non-equilibrium effects. Yeah? So to this end, yeah, you have to do this kind of transition from the microscopic to the macroscopic physics to assess basically whether we are in such a scenario, which is maybe the more generic one, or in such a scenario where really we go to a different fixed point. Yeah. So that's how I would look at that. Yeah. So it is good to have the right diagnostic tool on this mesoscopic or on the microscopic level of description. Yeah. Of course, the Lindblad equation, I mean, in this sense, there's always a deeper level or a higher energy model, which is purely a Hamiltonian coupled to a bath. Yeah. So, and but I mean, if we go to this Lindblad level, yeah, we can always be sure that the Lindblad generator already violates this equilibrium symmetry explicitly. Yeah? The reason is that, I mean, we have intrinsically a driven system, and so the microscopic Hamiltonian generator is already time periodic and not time independent. So that is, I mean, a way to rationalize why this Lindblad generator already doesn't have this symmetry. But in many circumstances, the point is that, I mean, yeah, we violate this a little bit, but at large distances, equilibrium conditions are emergent again. And then if you diagnose the symmetry on the level of the long wavelength action, you would actually see, oh, but this looks exactly like equilibrium again.
Okay, maybe let's thank Sebastian for the very next one.
It's like reversing action. I know how to